Hello everyone. Today's lectures we have see the topics phenols. In these topics we have studied the various types of reactions with phenols. The first reactions we have see the halogenation reactions of phenols. Phenols we can treat with in bromine. Then halogenation can take place at ortho and para positions. So 2,4,6 tribromophenol will get the product are here. If this phenol can treat with the Br2, that is the bromine water in carbon disulfide at lower temperatures to get only single product as parabromophenol. But in place of this bromine, we can use 3 molecules of bromine at room temperatures. So 3 position can be halogenation can take place at ortho and para positions. Like 2, 4 and 6 position bromination can take place are here. But if we use only single bromine molecules at lower temperatures to get only parabromophenol will get the product. If this resorcinol we can treat with the bromine, then bromination can take place at ortho and para positions. Similarly, the first reactions. We are see the last times the OH is act as an electron donating group and therefore its halogenation, that is electrophilic substitution reaction, can take place at ortho and the para position. Similarly, this OH group with respect to bromine is ortho position, this bromine also ortho position, and this bromine is a para position. If we consider this OH group, then this OH group with respect to ortho is a bromine, this ortho is a bromine, and para is a bromine. So these two electron donating group, so this bromination can take place at this position, this and this position will get the final product. Next reactions of alcohols are C is here. The acylation reactions of phenols means acyl group which is attached to this OH means this hydrogen and this Cl we can replace as a HCl as a byproducts. First reactions we are see, this is general reactions. This lone pair of this oxygen attack on this carbonyl carbon and replace this chlorine as a HCl, and to get acylation take place at the oxygen atom. Similarly, the other reactions we have take like this phenol can treat with the acetyl chloride. Then what happens? This hydrogen and HCl which is replaced this acetyl group which attach to the oxygens. So acetylation can take place at this oxygen atom and to get these products. Next reactions we are C is here. This phenol we can treat with benzoyl chloride. Then what happens? This Cl and hydrogen we can replace. So this benzoyl group which is attached to the oxygen. So these final reactions we can see the benzoyl group is attached to the oxygens and this is the product. Next reactions or another reagents we are used for acetylation like acetic anhydride. It is reagents are used as acetyl halides and another reagent is a acetic anhydride. Acetic anhydride, those reagents also used as for the acetylation of the phenol. Similarly, the acetylation can take place at the OH positions. So this is a general reaction. This acetic anhydride or any anhydride can treat with this phenol to get acetylation at these oxygens. Similarly, this phenol can treat with acetic anhydride, and then what happens? The acetyl group which is attached to this oxygen atom. So by using acetic anhydride also get acetylation reaction at oxygen atom. Next type of reactions we are see is here the Williamson synthesis reaction. You know that Williamson synthesis? The Williamson synthesis means is one of these salts and other is halide can undergo reaction to form dialkyl ether, which is called as a Williamson synthesis reaction. So first reactions like a general reactions we have see is here. This sodium phenoxide is a salt and this sodium phenoxide treat with alkyl halides. Then what happens? The O minus this attack on R and replace the X like NaX as a byproducts, and then alkyl group which is attached to the oxygen atom are here. So this is a final product is a ether, alkyl phenyl ether. Now next reactions we are see is here. This sodium phenoxide can treat with the methyl iodide in ethanol. Then what happens? This O minus attack on methyl group and the breaking of the CH3 iodine bond by replacing the I minus as a byproduct is sodium iodide and the alkyl group is attached to the oxygen. So this methyl phenyl ether will get the products. Similarly, the other reactions, the sodium phenoxide we can treat with ethyl bromide. Then what happens? This O minus of this phenoxide attack on this CH2 and replace the bromine. As a byproduct is sodium bromide, and this O minus is attached to the CH2CH3. So alkylation can be take place at oxygen atom. So it is a ethyl phenyl ether as the final product. Another reactions like this sodium phenoxide can treat with this allyl bromide. Then what happens? The O minus of this phenoxide is attack on this carbon and this double bond transfer is here and replace the bromine. So such a type of reaction can be done by using potassium carbonate. So this allyl group which is attached to the oxygen atom and to form allyl phenyl ether as the products. So these four reactions we are clearly indicate that by Williamson synthesis are very famous reaction to form this Williamson synthesis we are used to form the various types of corresponding ether derivatives. Next reactions we are see is here This phenol can treat with the caustic soda. You know caustic soda, sodium hydroxide are called as caustic soda in ethanol heating conditions. Then what happens? OH minus, which is strong base, therefore it's pick up this proton and to form these salts having a negative charge, sodium phenoxide. It is the salt. Similarly, this phenol can treat with the potassium carbonate. Then what happens? This potassium carbonate or carbonate take the protons and to form the byproduct is bicarbonate, and salt is potassium phenoxide as a salt. So this is not very important reaction, but still we enhance our knowledge for these reactions are very important. Next reactions we are see is here etherification of phenol. So etherification of phenol we can take place at in 3 steps. In first step what happens? This phenol, the another name is a beta naphthol. This beta naphthol can isomerize the bonds, can take place, and to this ketoenol tautomerism can take place. This is a enol convert to ketone. Then this methyl alcohol, the lone pair of this oxygen is attack on this carbonyl carbon to form negative charge on oxygen is here. So to form this negative charge, and then by using H2SO4 are here at ethanol conditions, what happens? This O minus convert to OAH. How will you convert this O minus? Pick up the proton from this and to convert the OAH. Then after H2SO4 is a strong or concentrated H2SO4, so HSO4 can pick up this proton to form carbon-carbon double bond is here and replace the water molecules. We know that the role of H2SO4 are the dehydrating agents, and therefore H2SO4 are used to removal of the water molecule. Dehydrating means the removal of water molecules and to get corresponding the etherification of the phenols. So these 3 steps we are used to etherify these beta naphthols. So what is the first step? First step is the ketoenol tautomerism. So this is a enol convert to ketone, and then after what happens? Methyl alcohol, any alcohol we have add, the lone pair of this oxygen attack on this carbonyl carbon to form negative charge on oxygen are here. Then after formation of negative charge on oxygens, these pick up proton from these protons and neutralize this positive charge are here. Then what happens? By using H2SO4, HSO4 pick up this proton to form carbon-carbon double bond is here. So by replacing, how will you replace? Firstly, the OH minus is converted to bad leaving to good leaving group by protonation. So firstly this protonated by taking the proton H plus, and then after HSO4 minus take the proton to form the carbon-carbon double bond is here, replace the water molecule. to got the ether of phenol.